All right, so we are going to use a paper circle to play with geometric shapes, and we're going to have a little fun with fractions and classifying geometric shapes. So here I have the best circle I could make out of a piece of paper, and this one I drew a circle in Google Drawing. Sometimes I grab a bowl out of the cupboard or a plate and circle and trace it and cut it out. But somehow for this activity, you need a reasonable sized paper circle. And the first thing we're going to do with our circle is we're going to fold it in half once. And so just fold it so one side gets to the other to the best of your ability, and then make that crease. And first thing I note is if I did a good job folding it, then what I should have here is a semicircle, which is half of the circle. So it has half of the area of the circle I started with. And if I open it back up, I can see that crease there, depending on the shadow. That's not bad right there. And that crease that we put in there happens to be a line passing through the middle of the circle, which is a diameter of the circle. So as we go around playing with our circle, we're also going to switch back to our notes here and make a note of some things that we've done. So we took out our cutout paper circle, we folded it in half. This is called a semicircle. How much of the area of the circle is in the semicircle? So it would be 1/2. Just going to write in that 1/2. And note, this activity is designed for elementary school kids, but it's not bad for adults too. When we open the fold for the new semicircle, what do you see about the folds? Oh, sorry, I can't read instructions quite right. Open and fold a new semicircle. And this is what we get. So I've got that one there, and you can fold it anywhere you want, except exactly where you did before. And like I mentioned a minute ago, I now have a new line through the circle. Since it cuts the circle in half, because I folded it in half, it's a diameter of the circle, because it makes a semicircle. And where do these two folds meet? Well, it's related, right? So they meet in the center, but then from the center to the edge means I have a bunch of radiuses or radii here. So just on your circle, make a mark on your center. Just a nice tiny little dot. We're going to need to refer to that center later. So one cool thing is a diameter is any line passing through the circle that hits the center. We have two diameters, so now we know exactly what the center is. With just one diameter, we didn't, but now we do. And we also have a bunch of radii. All right. So what do you see about the folds for the second semicircle? They meet in the center. Right? And just to confirm that, let's make another fold. So take your circle, fold it again somewhere, so that the circle gets folded in half, but on a different half. And what we should see is that that center point we marked is on that same line that we just made. So now I have three different diameters here. Side notes we might add here. Like you noted a minute ago, once I go from the center to the edge, that makes a radius instead of diameter. And if I have two different radii heading out, that forms a sector of a circle. So right here, this pie shape is a sector. So a sector of a circle is any chunk of the circle that comes with a vertex from the center of the circle. So again, terminology, diameter, line passing through the center. A radius would be from the center to the edge, and a sector would be any chunk of the circle that starts at the center and is made up of radii. So that's a sector. So let's back to our notes. What happens when you fold a third semicircle? I could say its diameter passes through the center. There's lots of things you could say here. And again, it's just emphasizing in the next question, all folds intersect at the center of the circle. Can you see why? And it's because they are diameters. And often answers to the questions come up later in this sheet. So I'm just going to write there each diameters. All right. So moving on to the next direction here, we're going to open up the circle. So mine's open here. And I want to fold an edge. Well, the circle is one big edge, right? So we're just going to take one part of the edge and we're going to fold it to touch the center. So what does that mean again? So here's my edge. I'm going to bring the edge down till it perfectly touches or goes through that center. Once I get it to that point, I'm going to come back and crease. So here I can see cut off part of the circle, but the fold I made, the edge of the circle passes through the center. And when I make that fold, I've now made a new line that passes through the circle. Now, any line passing through the circle, regardless of whether it hits the center or not, is called a chord. So we've just made a chord that is not a diameter. Okay. And let's see, what are we going to do next? So then it's just, there's no question here. It just says all folds passing through the center are called chords of the circle. So a diameter is a special chord that passes through the center. We're going to make a second fold. Okay, now this one's a little tricky. Make a second fold to the center. So like we did, but in a different place, so that the end of the new chord meets the end of the first chord. All right, so what does that mean? So right over here is the end of my first chord. My new fold has to meet perfectly right there and touch the center. So to make that happen, I'm gonna put that first fold back in, and then I'm gonna tease this so that I get a nice sharp point there without overlap, without bending the other chord, and I get to the center. So it's just a gentle balancing act there. I find most third graders can do this. Second graders are a little sloppy here. Okay, so I'm touching the center there. I got a decent sharp point that's not folding my other chord, and then I'm going to crease the paper. And I've got this new shape here. It's like an ice cream cone, or a snow cone maybe. So again, the goal was I can just barely make out the center there in the middle, and I have a sharp point where those two chords meet. Okay, so just a little gentle maneuvering there. Okay, open that up. We can see we have two chords that meet there. We're going to try to do that one more time. Okay, now a neat way to do that is to put those two folds back in, and then pretty much the middle of this curved side, if your circle is decent, you should be able to get to the center and meet the other two almost perfectly. So I get a decent sharp point on each edge without folding the other chords, and the edge of my circle gets pretty darn close to that center there. And we've made this beautiful new shape. So if your folds went well and you started with a circle, this should work out where each chord touches and each edge meets in the center. We've made a triangle. Is there anything special about this triangle?
It was a circle.
It was a circle, that's special. Is there anything else special about it maybe? No matter how I rotate it, it looks like the same triangle. I think all three sides are equal. Did I bring my ruler with me today? Ah, I forgot my ruler. What? I must always have a ruler on me. Crazy. It's an off day. All right, let's take a look at our instructions, see where we're at. So we made our first fold to the center and made a chord that wasn't a diameter. I'm trying to make a check there. There we go. We made the second fold, so it went to the center and met the first fold. That made the ice cream cone. And then we made a third fold that happened to meet both chords and met at the center. And now we have a three-sided figure with sides all the same length, and it's called an equilateral triangle. So all the sides are the same length. So that's what I was hoping we might notice there, that it is an equilateral triangle. All right, next, let's open up the circle. And what we have, if you can see the shadows of those folds, so that's the in, let's make it go the other way. The shadows maybe a little more pronounced that way. The vertices, so the point on a triangle is called a vertex. The vertices of the triangle are pretty much on the edge of the circle. So whenever you have a geometric figure whose vertices are on the edge of something like a circle, we say the figure is inscribed within a circle. Okay, so this equilateral triangle is inscribed in the circle. Okay, so inscribed inside, circumscribed would be outside. Okay, so this is inscribed in the circle. All right, let's see, what do we got next? So again, we have an equilateral triangle inscribed in the circle. With the equilateral triangle, find the midpoint of a chord by folding the adjacent vertices together. So again, let's go back to the triangle and some terminology. So I'm going to fold it back to a triangle here, and I'm going to put the folds underneath so I see the triangle, but not the folded parts of the circle. The points on a circle are called vertices or singular vertex, and the side of a circle is called an edge. Triangle. There we go. So this figure is a polygon. It's a triangle because it has 1, 2, 3 edges and 1, 2, 3 vertices. What we want to do is find the midpoint of one edge, and we can do that by folding two adjacent edges together. So I'm not going to fold it in half completely. I'm just going to crease the very bottom there to figure out where the center is. And I'm going to make a little mark on that spot. Okay. So I made a little pen mark on my center of that side. And what I want to do here is I want to fold the opposite vertex. So for that side right there, these two vertices are adjacent to each other. And from that side, this vertex is opposite. I'm going to fold the opposite vertex to touch that midpoint. So mark that there, come back and crease across. We've made a new geometric figure. This is no longer a triangle. It has 1, 2, 3, 4 sides. So at first glance, it is what's called a quadrilateral. Quadrilateral is a 4-sided polygon. Now, this actually has another cool property that makes it a special kind of quadrilateral. There's actually has 2 special properties. Can anyone name one of the special properties? The sides opposite my fingers, they look parallel to me, like they're going in the same direction. If they extended forever, they would never intersect. So if you have a quadrilateral with a pair of parallel sides, it has a special name. Starts with a T. R. Trapezoid. Yeah, we get 2 winners. Nice. Yeah, we've made a trapezoid.
Yes.
Cool. Yeah, so a 4-sided shape that has a pair of parallel sides is called a trapezoid. Now, in some books, when they define trapezoid, they say exactly 1 pair. Other books say at least 1 pair. So there's like 2 different competing definitions for what's a trapezoid. I usually go for at least 1 pair, and we'll talk more about that in a minute. So here I have a trapezoid. Now, even better, I think when I hold the parallel sides so they're horizontal like this here, I think the left side and the right side here, I think they're the same length. So that means it is an isosceles trapezoid. So isosceles means it has 2 equal sides. So like this equilateral triangle is also an isosceles triangle because it has a pair of equal sides. And this trapezoid would be called an isosceles trapezoid because it has the parallel sides making it a trapezoid, and it has the equal or congruent edges is the more precise thing to call it. Since it has a pair of congruent edges, it's isosceles. All right, so let's see, where do we go? We brought the tip of the top to the midpoint, and that formed a trapezoid. And even more specific, it's an isosceles trapezoid. So isosceles trapezoid. And I have to mispronounce isosceles to spell it right.
I do that with so many words when I'm spelling it out, like Pendleton, I have to say Pendleton.
That's a good one. When I was in third grade, my teacher taught me to say People to make sure I got people right.
Yeah.
I just wanted it to have two E's instead of an E and an O. All right. Ooh, this is an interesting one. The area of the trapezoid is what part of the equilateral triangle? Ooh, okay. So here's the equilateral triangle. We fold down that top. Okay, so the area of the trapezoid is smaller. What part is it of the original equilateral triangle? Well, let's see. In this figure right here, I see 1, 2, 3 triangles of the same size. And when I fold it up, there's a fourth one. So I think the trapezoid is 1, 2, 3 fourths. Does that make sense? Of the equilateral triangle. Cool. And some ancient people, like the Greeks, did a lot of amazing mathematics. They didn't measure things in like square feet like we did. What they did is they just said, what part is one figure of another? So they wouldn't say that this is so many square inches. They didn't have inches, but they would say, oh, this figure is 3/4 of that figure. Okay, so the area of the trapezoid is what part of the equal triangle? It is 3/4. Let's see, what else do they have to tell us here? The line connecting the midpoint of the two sides of the triangle is parallel to and equal to 1/2 of the base. Ooh, let's think about that. The line connecting the midpoints of these sides. So when we picked the midpoint here and we folded this down to the midpoint, we created two other midpoints, which is kind of cool. And those other midpoints, the length across here, if you think about it, is 1/2 because the bases of these two triangles is the same as the base of that triangle. That's kind of cool. A lot of interesting symmetry going on here. All right, ready for more fun with the folds. All right, cool fact. Cool fact. With the trapezoid, fold the vertex of the original triangle to its opposite vertex. Okay, let me think about this for a sec. With the trapezoid, here's my trapezoid. Fold the vertex of the original triangle. Okay, so the trapezoid has 1, 2, 3, 4 vertices. These two top ones here, the shorter side, I'm saying that's the top. Those weren't vertices on the triangle, right? That was part of the straight line there. These two are vertices of the original triangle. This vertex and this vertex, these two are adjacent to each other. Adjacent means they're connected by an edge. So this far one over here would be opposite. So this is adjacent to that one's opposite. What I want to do is I want to fold this tip to that adjacent one. And the paper is going to resist a little bit, but I think we can get pretty close. And they should sit almost on top of each other. All right, that's the best I can do. There, crease it. Ooh, I've made a new shape. Fold it this way. What is this sucker?
A rhombus? Is that what they're called?
It is a rhombus. Yes, that is called a rhombus. Some
I
people
didn't
call
see
it
a diamond.
Yeah, some people call it a diamond. And it turns out diamond means a lot of different things. So there isn't technically a polygon called a diamond. There is one called a kite. So it turns out this is a kite. It's also a rhombus. It's also a parallelogram. And by some definitions, it's also a trapezoid. So there's lots of names for this. I think the best name for this one is a rhombus. Okay, what is a rhombus? All right, so a rhombus is a quadrilateral. It has 4 sides, and all 4 sides are the same length. That's what makes a rhombus. So a square is a kind of rhombus. This rhombus is definitely not a square though. Agreed? Right, it doesn't have right angles. Squares have right angles. Yeah, so this is called a rhombus. And I believe that each edge, sometimes we call them sides, are congruent, the same length. And just kind of open this back up again. So here's my original triangle. I bisected this bottom side. So these, it's now in two equal pieces on each side of that dot. When I folded that down, that coincidentally bisected this side. So I'm going to make little dots there too for fun. So there's a bisection of that side or edge, and here's my bisection of that edge right there. So this triangle now is made up of two equal pieces on each side. And folding it back into the rhombus, I now have four of those same lengths here. Okay, let's see. What questions are we asked about this right here? The trapezoid, with the trapezoid, fold the vertex. Okay, we did that to its opposite edge. This figure is called a rhombus. Rhombus has an RH, O-M-B-U-S, rhombus. All right, next question kind of gives that away. It's a rhombus. The area of the rhombus is what part of the equilateral triangle? Oh, okay. Well, the rhombus has two of these triangles here, and the original had 1, 2, 3, 4 of them. So we could say it's 2/4 or 1/2. Either way works. The area of the rhombus is what part of the equilateral triangle? I'm going to call it 2/4. Or we could say 1/2. Or you could just pick one of those. The area of the rhombus is what part of the trapezoid? Oh. Okay, so here's the trapezoid. It has 1, 2, 3 pieces. The rhombus has 2 of those. So the rhombus is 2/3 of the trapezoid. That seems reasonable. All right, the area of the rhombus is what part of the trapezoid? 2/3. What if I switch that question? What if I said the area of the trapezoid is what part of the rhombus? Trapezoid's bigger, so the fraction would have to be improper. It would be, well, how many pieces are here? Out of 2. So
Three halves.
Yeah, 3/2 or 1.5. Yeah, there we go. Yeah, cool. Okay. Uh-oh, my directions got cut off. Let's see. Well, let's see. The sides of a rhombus are all equal. Opposite sides are parallel. Opposite angles are equal. So that's a nice coincidence. A rhombus is a subset of the parallelogram. All right, now let's see. I need to double check my instructions. Was my piece of paper didn't print right? Where did I put my instructions? Over here. All right, with the rhombus, fold the last vertex of the original triangle to its opposite vertex. Okay. Back here to my picture. So here's the rhombus. I want to fold. So this down here for me is my original edge of the or vertex of the triangle. I want to fold it over to its opposite vertex. And it almost sits on top of each other. The thickness of the paper is getting in the way a little bit. Origami paper might be a little better for this, but that's okay. What is that? Well, I'm pretty sure based on those midpoints we marked earlier, this is another equilateral triangle. All right, what were my instructions here? Okay, so it's another equilateral triangle is what we can write there. Just gonna sneak that on the bottom of my paper here. Another equilateral. There we go, triangle. Did yours get cut off too at the bottom? Okay, I must have accidentally upped the magnification when I printed this version. All right, and then what else were we asked? The area of the new triangle is what part of the original? Well, 1/4. So it would be 1/4 of the original. Squeeze that in here. It is 1/4 of the original. Cool. All right, here's the coolest thing. Check this out. So mine is kind of floppy right now. If you gently push those little triangles up so they touch together, you're going to get this beautiful three-dimensional shape. Look at that. Isn't that gorgeous? Makes me want to get some tape and make it stay like that. Anybody know the name of this shape? It has 1, 2, 3, 4 flat triangle faces.
Pyramid.
It is a type of pyramid. It's called a triangular pyramid, but it turns out there's another single word name for triangular pyramid. It is called a tetrahedron. Cool one, huh? Never heard of a tetrahedron? Yeah, this is a tetrahedron. And it is a triangular pyramid. The Egyptian pyramids have a square base. This one has a triangular base, which is pretty cool. All right, and I believe that might be, to get to that yet. Oh, I'm ahead of myself on this, I think. Yep, okay. We got a bunch more questions to answer. The area of the new triangle is what part of the trapezoid? Okay. The new triangle is this one right here. Right there, and it is what part of the trapezoid? Well, that would be 1 out of 3 pieces. So that one's 1/3. The area of the new triangle is what part of the rhombus? Okay, it is 1 out of 2, which is 1/2. The area of the new triangle is what part of the new triangle? Oh, that's sneaky. How about just 1 out of 1 or 1? Okay, now we're switching things the other way. The original triangle is blank times as large as the new triangle. Well, the ratio there would be 1 to 4. So we would say 4 times as large. How about the trapezoid? It's how many times? Well, the trapezoid had 3 out of 1, so that'd be just 3. The rhombus is blank times as large as the new triangle. That would be 2 to 1, or just 2. Okay, now we're getting a little trickier. The original triangle is blank times as large as the trapezoid. All right, original triangle, trapezoid. So the original had 4 pieces, the trapezoid had 3, so we would say 4/3 would be that ratio. So it's 4/3 times as large as the trapezoid, and blank times as large as the rhombus. The original triangle compared to the rhombus. 2 to 4, or 4 to 2 would be the ratio, which we could simplify to be just 2. All right, and here's where I got a little bit ahead of myself. When we take the vertices of the triangle and along those folds, we get them to touch, then this three-dimensional figure here is called a tetrahedron. And the answer to that question is right below it. Tetra, like I don't know if you ever played a game called Tetris.
Yeah.
Tetris is made up of all the shapes that you can make with 4 squares, where the squares touch at least one edge. So tetra is a prefix that means 4, and hedron. Anyone ever heard the word hedron before? Hedron means flat face. So tetra means 4, hedron means flat faces. So it's a 3-dimensional figure with 4 flat faces. Okay, like a cube has 6 flat faces, so it would be called a hexahedron, as a fancy name for a cube. Okay, let's see. Tetrahedrons have all surface areas congruent. This tetrahedron does. It has 1, 2, 3, 4 faces, and those faces are all the same congruent shapes. They have all the same area. So it's got some nice features there. Other interesting things about this tetrahedron is all of the edges where the sides meet are all the same length. And all of the angles where any two edges meet are the same measure also. So, which is pretty remarkable. When we'll get to that more when we talk about 3D shapes. All right, ready for more fun with folding. Open the figure to the original triangle and fold one vertex to the center of the circle. All right, let's see. Open it up. Undo those creases a little bit. So originally we folded a vertex to the middle of the opposite edge. This time we're going to fold the vertex to touch the center. And then do your best to crease. So, oops, a little off there, but close enough. Okay. What is this? Well, let's see, it's got how many sides? 1, 2, 3, 4. It's a quadrilateral. The way I have it oriented here, I have a bottom and a top. We go that way. And it looks to me that the bottom and the top are parallel. So if I have a four-sided figure with a pair of parallel sides, we call it a trapezoid. I'm also thinking, due to the symmetry I got going on here, that the right and left sides, or left and right sides here, they look about the same length. Which, like before, I just have a new isosceles trapezoid. This one's a little bit bigger. Okay. And I skipped a question. We'll go back and answer that in a minute. So let's see. We formed another isosceles trapezoid. Another isosceles trapezoid. Let's see. The top base of the trapezoid is blank the length of the bottom base. Ooh. That I don't know. And then we'll go question I missed. All right. So with the first trapezoid, the top base was half of the bottom base, or the bottom base was twice. This side edge up here is definitely smaller. So how many of these small ones fit in the big one? Well, if I'm not going to crease it, but I'm going to kind of bend it to be down there. It looks like that's thirds. I make a mark right there and right there. I think I've just split this bottom into 3 equal length pieces. So I'm guessing, I don't have proof yet, but I think the top base here is 1/3 of the bottom base, or if we go the other way, this is 3 times the shorter base. And side note on trapezoids, the parallel sides are each called bases. So base 1, base 2. So I am guessing it's the top base, the length of the bottom base. So I'm calling the little one the top, the big one the bottom. So I'm going to say 1/3 there. If you orient it the other way, it would be 3. So I'm going to draw mine in here. Looks something like that there. So I'm pretty sure that's thirds. Okay. I missed a question back here about the tetrahedron. What is the surface area? What is the surface area of the tetrahedron if the original triangle is 1? So they're telling me the original triangle has an area of 1. What's the surface area of the tetrahedron? Well, if I paint the tetrahedron, then I've painted the whole triangle. So it's also 1. It's the same. All right, so back to the new isosceles trapezoid. We want to fold a second vertex to the center of the circle. All right, so from the original triangle, let's go this way. So here's my first fold to the center. I'm just going to take one of those other vertices and fold it to the center. It's close enough. Okay, what have I made? Now this thing here looks kind of like a diamond to me. Let's see, how many sides does it have? 1, 2, 3, 4, 5 sides. What do we call a 5-sided figure like this? Pentagon? Exactly. This is a pentagon. Pentagon. What is a pentagon? Pentagon is a 5-edged or 5-sided polygon. Poly means many, gon means edges. Edges is a straight thing. So any plane figure with straight edges is some kind of polygon. Since this has 5, it's called a pentagon. Some people call it a 5-gon. That's okay too. But the more popular name is a pentagon. So there's my pentagon. Fold the third vertex. Okay, so 2 of my vertices got folded to the center of the original triangle. I'm now going to fold the third one in there. Oh, cool. What is this shape? Isn't that beautiful? This might be my favorite geometric shape next to a circle. It's got 1, 2,
Hexagon?
5, 6. Yeah, it is a hexagon. Woo. That one was given away here too. Hexagon. Now, actually, there's a better name for this than a hexagon. Actually, it's got like 2, it's a 2-word name. Some things to note about this right here. Based on the way we folded it, each of these edges here are the same length because they all came from folding this point of the triangle down. And since it was an equilateral triangle. So I have 6 equal sides. Not only that, because it was an equilateral triangle, each of these angles here are the same angle measure. They're all equal. Anytime you have a polygon that has all the same length edges and all the same interior angles, it's called a regular polygon. So this would be a regular hexagon. I'm just going to parentheses here and just put regular next to it. And regular means equiangular and equilateral. So regular, equilateral, and equiangular. Equiangular. And sometimes I get asked, well, if it's equilateral, doesn't it have to be equiangular? Well, it depends. Like for a triangle, if it's equilateral, it turns out it has to be equiangular because triangle is what we call rigid shapes. We'll explore rigidity later. But check out the rhombus. It has 4 equal sides, but the angles aren't all the same. It's got 2 different interior angles. So the rhombus is equilateral, but not equiangular. What would happen if I made the rhombus equiangular in addition to already being equilateral? What shape would I get? Imagine that we could kind of squeeze this to be also equiangular. Try to picture that in your head. What would it be? It would be a square. Nice, yeah. So a rhombus isn't regular because it is equilateral, but not equiangular. But it's still awesome. Okay, let's see, where are we? Oh, now we're going to do some areas. The area of the hexagon is blank that of the original triangle. Okay, let's get back to my hexagon here. Okay, so the hexagon is definitely smaller than the original equilateral triangle. How much smaller? What part? Oh, interesting. With those folded in flaps there, the hexagon looks like it's made up of 6 equilateral little triangles. How many of those little triangles does the original one have? Hexagon has 6.
3?
Not
no?
quite. So check it out. So the hexagon has 6, right? So I can see the 6 here. 7, 8, 9. The original triangle has 9 of these little flaps right there. Yeah.
Oh, God.
Right, not the big flap, the little flap. Yeah, so here, and so I'm gonna actually trace these in here to see them. So let's do that. And feel free to draw on yours or not. Okay, so I can see the 6 triangles inside, and then if I draw on these folds too, then I can see the original has those 6 plus the 3 on the outside, or 9. So the hexagon is 6/9 of the original triangle, which we could also call 2/3 on a good day, I think. Let's double check that in a minute. All right, so I'm going to go with 6/9 as my answer because I can see the 6/9. And just thinking about off to the side here, 6/9, they're both divisible by 3. So that would be, yeah, 2/3. I was right. Sometimes I got to put it on paper too to see it. The area of the hexagon is blank that of the second trapezoid. Okay, so the first trapezoid was this one where the fold went to the midpoint of the other side. The second trapezoid was where the flap went to the center. All right, so here's the second trapezoid versus the hexagon. The hexagon is smaller. It has 6 pieces. How many pieces does the second trapezoid have? 6 plus 2, 8. So then it would be 6/8 of that trapezoid, which we could enter as 6/8, or we could reduce it. I'm going to enter 6/8 because that's what I visually see. What would that be? 3/4 would be another fine answer there. Oh, we also made a pentagon. So we're also asked here, the area of the hexagon is blank that of the pentagon. Okay. The hexagon is this, the pentagon is 1. So the hexagon is 6 out of 7 pieces in the pentagon. 6/7. And blank that of the small triangle. Okay, so we've got a lot of triangles floating around. We've got the big triangle. We've got this small triangle, and then we have this kind of intermediate triangle that we found second. So the big one, the second triangle, and now we got this third one. So we want to know, the third one's the small triangle. So the hexagon is blank that of the small triangle. Well, the hexagon is 6, the small triangle is 1 of those pieces, so it's 6 out of 1, or just 6. All right, here's where things get wacky and a little more hard to think about. So before we had so many folds, this made a nice tetrahedron. But now when I kind of push the edges, they're not quite making a tetrahedron anymore because I have these extra flaps, but I can kind of stick these flaps into each other using the way mine is going here. I have those circle flaps that are sitting there. So I can tuck the point inside the circle flap. Yours may be underneath. I'm going to try to tuck that in and push them together. And then I'm going to push that one in. I've got this new interesting shape here. What? It looks like the tetrahedron with the top chopped off, doesn't it? Geometrically, when we chop something, we call it truncated. We just truncated the tetrahedron. This is a truncated tetrahedron. And when we do some more 3D stuff, 2 popular things to do to 3D shapes are to truncate them, chop part of it off, or to pull a tetrahedron out of a side, and that's called stellating. So later we'll look at some stellations along with truncations. So this is a truncated tetrahedron. All right, and I give that name to you right here, truncated tetrahedron. And now we're going to try and answer some questions about the surface area. Okay, so let me see. So I could paint this truncated tetrahedron. And I'm asked its surface area, so that's the paint it would take. So it has, well, how many sides does it have? It has 1, 2, 3, 4, 5 faces that get painted. That area is blank of the original triangle. So if I painted those, but not the original triangle, there's some parts of the original triangle that would be unpainted. Let's see. To make the truncated, these 3 flaps cover each other up, right? So I'm only painting 1 out of 3 of those flaps. I'm losing 2 of them underneath, right? Okay. How many of these flaps are in the original triangle? Oh, I've got it drawn right here. Right, there are 1, 2, 3, 4, 5, 6, 7, 8, 9 of them. The truncated tetrahedron loses 2 of them. So it must have 7 of those total. So I think the truncated tetrahedron, because those 2 get covered, is 7/9 of the original. I think so. That sounds right, doesn't it? Okay. 7/9. All right, so again, for each of these, we're comparing to the truncated tetrahedron. The truncated tetrahedron is blank that of the smallest triangle. Okay, so let's see, we just determined that the truncated tetrahedron is made up of 7 of these little triangles because 2 of them get covered, 2 out of the 9 we have. So the truncated tetrahedron must be 7 times that original, that little triangle right there. So the truncated tetrahedron is 7 times that of the smallest triangle. What is that? That is the area. Okay, the truncated tetrahedron is what that of the second trapezoid. Okay. Second trapezoid was this one right here. And that trapezoid right there, the original has 9 of these little triangles. So this must have 8 of them. The truncated tetrahedron has 7, so it's 7/8. That wasn't too bad. 7/8. Uh-oh, I think this might be getting a little harder. The surface area of the truncated tetrahedron is blank that of the first trapezoid. Oh boy. Okay, so the first trapezoid was a totally different fold. So here's the first trapezoid. The truncated tetrahedron is really the same surface area as my pentagon, because the pentagon has 7 of those little ones. Now the problem is those little triangles right here, they don't really line up well with the big triangle here. So here I can see how they're related. So let me fold all of these in. So here's my medium-sized triangle. If I draw this crease in here, should have got a ruler. Oops, that's a little off right there. This side looks more than, that doesn't look like I cut them in half, does it? So we got to find a way to compare this area to the whole area. It looks like this one is more than half of the medium-sized triangle. So right now we have 3 triangles to work with, right? We have the original big one. We've got this medium one, and we have this smaller one. Somehow we have to find a way to compare the small and the medium triangle. Oh, wait a minute, I see something in my other folds. Check this out. So remember earlier I drew in my hexagon divisions? If I also draw in the creases for my first set of folds, I'm starting to see another triangle living in here. Oops, I'm not doing a very good job. This triangle right here. That triangle looks special. It's also right here, right? And right here. Oh, wait a minute. I think I see more. It looks to me, check this out. Let me fold these the other way. Like that. And if I just look at that center medium-sized triangle, if I just cut across like that, there, and that there. So I'm taking my hexagon lines with the second fold lines and adding some new ones. My medium, so now I have an extra small triangle. So how many triangles do we have altogether? Big, medium, small, and extra small. How many extra smalls are in my medium? 1, 2, 3, 4, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9 of them. Well, that's some cool symmetry. There's 9 there. How many of those live in this triangle here? Well, I think, see, I'm running out of colors here. Choose a pencil. I think that's this right here. I think there's 1, 2, 3, 4 of them there. That would be this top part here. So if we just kind of go across like that, so this line keeps going right to there. Check that out. Oh yeah, look at that. That's cool. I wish I had a ruler. I could go next door and get one. But I'm just captivated by this. Okay. If we extend these lines, okay, then we got to figure out how the hell did Gary get here again? How many of these extra small triangles do we have in the big one? Well, let's go back to the middle one here. In the middle one, a minute ago, I counted there were 9 of them. So there's 9 in these other 3. So I have 1, 2, 3, 4 of these. Each of them have 9. 9 times 4 is, all right, 36. There's 36 of these extra small triangles living in here. 4 of them live in my small triangle. How do I get my small triangle again? Right there. 1, 2, 3, 4. And 9 of them live in my medium triangle. Okay, so let's write down some conclusions here. We have 4 different triangles we found. We have the original. We have what I was calling the medium triangle. We have what the small triangle from the hexagon. And then when we tried to match the small and the medium together, we got an extra small triangle. Extra, oops, small. And if I say the extra small is like 1 unit, the small one had 4 of them, the medium one had 9 of them, and the original 36. So it looks like I can use this extra small one to compare any 2 shapes that we made. This is like finding a common denominator with fractions, which is fun. All right, so I'm going to stop there with this. I'm going to leave it up to you based on those scribbles to try and answer these last 2 questions, and then come up with a comparison that wasn't asked already. It's something you can do there, and there's plenty of others to do. I want to go back to this for a minute to show those triangles one more time. And let's see, to do that, I'm going to fold mine in the other direction. Summarize this. Okay, so my first set of folds was when I took a vertex of the original triangle to the center of an opposite side. And when I did that for all three of those, then I get these lines right here. Then we folded a vertex to the center. And we did that 3 times in a row and got ourselves a hexagon. And this is when I originally started drawing things in. I traced in those guys to see the hexagon was made up of 6 of those. And then after that, I noticed that those 2 sets of drawings I made this new extra small triangle right there. And that I can extend those out and get a bunch more triangles for comparison. So I'd recommend kind of playing around with that next.